First I told you that we talked about a general 3D stress tensor. We figured out that there are 9 components for a stress tensor, and out of them 6 components are independent. In 2D that will actually be 4 components. Complementary shear stresses are equal. And after that we took a bar and we applied axial forces on it, force P, and we tried to find out the stress tensor at a point. How did we do that? So here we would like to know, depending on the coordinate we take, how the stress tensor changes. So we had taken a plane which makes theta degree with the vertical, and we found out the normal stress and shear stress in those planes. So these were the equations we obtained, and we found out the maximum value of normal stress and shear stress. So here we can see that depending on the angle theta which the plane makes with the vertical, all these quantities changes. It's a function of theta, right? P by A cos square theta means it's a function of theta. So it does change depending on our coordinate. Now let's see how we can use the idea of Mohr circle to better understand the idea of stress transformation. So let's first take an example. Oh God, stuck. Okay. So let's take a state of stress where you have a point. On that point you have normal stresses 1 MPa and 3 MPa. Is it from here? Okay. And you also have a value of shear stress, which is 2 MPa. So by convention, these direction will be taken as the positive directions of stresses, normal stress and shear stress. Now let's see what happens when we change the coordinate. Means what happens if we rotate this this control volume by an angle theta, and that is what we try to understand in the previous problem. But let's see how we do that for a general case. Let's say we make a cut. We'll make a cut in the control volume through that line, and this is an enlarged view of the same element. Now let's say this is angle some angle, let's say 25 degree. Now how do we find out normal stress and shear stress here? So this doesn't look difficult, right? Because what we need to find out is sigma and tau here, and this is a 2D system. So we can find out the equilibrium equations for x direction and y direction. And if we do that, we have two equations and two unknowns, which means we'll get the value of sigma and tau. So this is something you need to do. Let's say this is your homework, right? So I hope you must this is something you should finish, something you would do for the next class. How do you solve this? You just use the equations, right? Equilibrium equations. The things you need to take care here. How do you write down the equilibrium equations here? So the net force in x direction should be 0, but forces are not given here. What we actually have are stresses. So what will be this angle here? that will be what? This angle will be 90 minus 25, and of course this will be same 90 minus 25. This will be 25. So only thing you need to take care here is that remember here is that you need to multiply the stress with the area to find out the force. So 3 MPa multiplied by area. So you can assume that it has a unit depth, and let's say we are making a so since this angle is 90 here, and this angle is 25. Now here what will be this angle? That will be 90 minus 25. So you know all the angles. So you know the ratio of length of sides. So the area is length of side multiplied by the depth. So depth can be assumed as what? Just what? So multiply each stress components with the corresponding area and equate them. You will get the equilibrium equations. So here this will be 25, right? This will be 25. In x direction this will be minus sigma cos 25 minus sigma cos 25 multiplied by this area. That should also be considered. If you take this as 1, this should be 1 cos 25 area. I mean the area should be 1 cos 25. This should be 1 sin 25. So that's how you find out sigma and tau here. For this particular problem, please find out these values sigma and tau by the next class. Now let's come up with the general equation for stress transformation. So this is similar to what we just did here. So we, instead of using actual values, we will use variables, and we'll try to find out what will be sigma and tau for a plane which makes an arbitrary angle theta with the vertical or horizontal, which let's see what is convenient. Okay. So for the state of stress, for a sample state of stress, you have normal stress values sigma x and sigma y, and this is tau ix, this is tau xy, and they are equal also, but anyway we'll write that here. This is the state of stress. Now what we are going to do here is that, okay, it's better to so this is the first one. This x and y are the coordinate system for this state of stress. Now what we do is that we will rotate the coordinate system by an angle theta, and we will get a new coordinate system which we will represent it using these two, x dash and y dash. Now we will try to find out what is the state of stress for this rotated coordinate system. How will we find out that? So for a rotated system, this will be the element. So this will be sigma y dash, we'll call that. So this is sigma y dash, sigma x dash, tau xy dash, tau yx dash. Same thing on the other side. So we have this here, and we need to convert it to this. Now the question is, how do we do this? We will use the same strategy. So we will make a cut here. In the first element, and what will be this angle? This will be theta, right? Same theta, parallel to this axis. We'll make a cut here, and we'll find out the equilibrium equations for this part, and from there we'll find out sigma x value. See, sigma x is parallel to this line. So once we do the cut, we'll get the value of tau xy dash and sigma x dash. This is the cut part, and here you have sigma x, tau xy, tau yx, sigma y, sigma x dash here, sigma x dash here, tau x y dash, and this angle is theta here. So we will use this to find out equilibrium equations. Okay, let's take a new page. I think I'll put this here. So this angle theta sigma x dash to xy dash to xy to yx sigma y. So this is the these are the stress components. Now let's use the equilibrium equations. So net force in x direction should be 0. So how do we find out the forces here? All we have are stresses. So let's assume that this area is dA. So in that case, the force due to sigma x dash will be sigma x dash into dA. That is equal to, now what will be, now let's consider all components in the horizontal direction. So some of them are in fully in vertical direction. For example, sigma y is fully in vertical direction, tau xy is in fully vertical direction. So we don't need to consider them. For sigma x is fully in horizontal direction, but towards left. Towards left means here will be plus. It should have negative sign. Plus negative sigma x into area should be the term here. Okay, that's actually a problem, because when we do that, we'll get to sigma x dash and tau xy dash in the same equation, which will be a trouble. We don't want that. So we'll actually take equilibrium equations in x dash direction. So this is the x dash direction. So what is the advantage of that? If you take x dash direction, this will be this. There will be no cos or sine component for sigma x dash dA. Sigma x dash dA will be the term, and you can simply equate the whole term with sigma x dash dA. So this will be equal to sigma x dA, sigma x dA cos theta. If this area is dA, this area will be dA cos theta. So stress multiplied by corresponding area will be the force due to the term, due to the stress sigma x. And what will be this angle sigma x makes with x dash? That will be theta. So cos theta of this whole term. So why do you have two cos thetas here? First cos theta is associated with the area. dA cos theta is the area here. And sigma x dA cos theta is the force. The component of force in x dash direction is found out by multiplying it with another cos theta. This angle here is considered there. That's the reason why you have two cos thetas. Now same thing can be done for sigma y. Sigma y dA sin theta will be the area here. Sigma y multiplied by dA sin theta multiplied by sin theta will be the force in x dash direction due to sigma y. Similarly, tau xy and tau yx should be considered. Tau xy is acting on this area, so we should multiply it with the dA cos theta, and component of that in x dash direction will be the whole thing multiplied by sin theta. Why sin theta there? If this is theta, this is 90 minus theta. So cos theta here and sin theta here. Again, tau xy, both tau yx is equal to tau xy, right? So you can write the same thing. So for other term also similar equations will come out. This other stress will be acting in the plane dA sin theta. So that is the corresponding area multiplied by cos theta. So this will be the whole equation. Now you have cos square theta here and sin square theta here. So the term will be sigma x cos square theta plus sigma y sin square theta plus 2 tau xy sin theta cos theta. So this is the whole equation. Now let's do some trigonometric operations. We know that cos square theta is equal to 1 plus cos 2 theta by 2, and we know that sin square theta is equal to 1 minus cos 2 theta by 2. And sin 2 theta is equal to 2 sin theta cos theta. So 2 sin theta cos theta is replaced by sin 2 theta. Now if we rearrange okay, what is missing here? Yeah, Nothing, it's correct. So sigma x dash is equal to this. What happened to dA? dA was simply cancelled out. Now we will see that sigma x dash is equal to sigma x and sigma y can be taken together. So sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 multiplied by cos no, not cos 2, yeah, cos 2 theta, right? Cos 2 theta plus tau xy sin 2 theta. So this is the general equation to find out sigma x dash here. So if you remember the first problem I have given you, you can actually use the equations here to find out sigma and tau. But I recommend, for this problem I suggest using equilibrium equations. So I want you to have some practice there. You must not use the direct equation here. So let's for a general case, general state of stress, general means a 2D state of stress with normal stress of sigma x, sigma y, and shear stress tau xy. The sigma x dash, which you obtain by rotating a coordinate by an angle theta, will be equal to this quantity. Now similarly we have to also find out tau xy dash. So the exact same thing will be done. In the first case we have taken equilibrium equations in the x dash direction. The second case you have to take it in the y dash direction. So the exact same procedure can be followed, and you will see that. So I will not do it here. Sigma forces in equatorial force in y direction, y dash direction, and you will get sigma x y dash equal to minus of sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. Now if you see these equations here, you can see that here you have minus sigma x minus sigma y by 2 sin 2 theta no, I'll also write down, I think I'll write down everything here just to be very clear. So I'll just rewrite the equation for sigma x dash here. Sigma x dash is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta, right? Cos 2 theta plus tau xy sin 2 theta. Same procedure can also be followed to find out sigma y dash, and that you will get as sigma x plus sigma y by 2 minus So same procedure means what procedure will you follow to find out sigma y dash? So you have to take a plane. Sigma x dash you obtained by you taking this plane. So for sigma y dash you have to take a plane perpendicular to that to cut the element and find out the equilibrium equations. So here an interesting fact here is if you simply add up sigma x dash and y dash, sigma x dash and y dash, what happens? These two cancels out. This also, okay, this is actually negative, okay. These two also cancels out. So you will get it as a sigma x plus sigma y. So whatever angle you take, the sigma, if you add up sigma x dash and sigma y dash, that will be equal to sigma x plus sigma y. So that is that basically remains the same for all values of theta, and that's something that's a fact will be very useful for you in the future for doing problems. Now let's just like the previous cases, we'll find out the maximum normal and shear stresses, and we'll find out for what value of theta this happens. So let's consider sigma x dash first. What will be the maximum value of sigma x dash? And you have to find the derivative. Derivative must be equated with 0. So if you sigma x dash d sigma x dash d theta must be equated to 0 to find out the maximum value of sigma x dash. And what will be that? The first term is gone. Here you have a term sigma x, so that will be sigma x minus sigma y by 2. Derivative of cos 2 theta is minus sin 2 theta. 2 right, 2 sin 2 theta. And derivative of sin 2 theta will be 2 cos 2 theta, right? So this is equal to 0. So you can take one term on the other side, and this theta, okay, we will call it theta theta 1. Okay, we'll first find out theta and we'll put it. Take it on the other side, divide sin theta with cos 2 theta, you will get tan 2 theta as tau xy divided by sigma x minus sigma y divided by 2. So this is the angle, what is the angle? 2 theta. Theta is equal to half of tan inverse. This quantity will be the angle for which you will get the maximum value of sigma x dash. and these maximum stresses are called principal stresses. And the plane on which this maximum value of stress act are called principal plane of stresses. So for a maximum value of sigma x dash, there will be a corresponding minimum value of sigma y dash which occur for the same state of stress. And both of these stresses are actually called principal stresses. So if you simply substitute this value of 2 theta back in this equation, how will you do that? You can take no, that's a bit time consuming process. So what you'll do here is that we will put this value of theta back here in the equation, and we'll find out what is the maximum value of sigma x dash. And here you will use the fact that theta, how will you, theta is nothing but half of tan inverse of this quantity. So we will use the corresponding triangle and the ratio of each sides to use to actually find out the value of sigma x dash. So I'm thinking whether should I do that or not. It takes some time for us to actually do that. Okay, I'll just tell you what happens here. So this is let's say this is 2 theta, and this is tau xy, and this is sigma x minus sigma y by 2. So what will be this length of this side? That will be tau xy square plus sigma x minus sigma y by 2 whole square root. This will be the length of this side. So this correspond with this equation, right? Tan 2 theta. Tan 2 theta is equal to opposite side by this side, adjacent side here. Now if this is tan 2 theta, you can find out the corresponding equations for cos 2 theta and sin 2 theta and replace it here. Cos 2 theta will be this value divided by this value. Sin 2 theta will be this value divided by this value. So you can actually see that will become, sigma x minus sigma y by 2 whole square divided by this term, and similarly sin 2 theta tau xy squared by this term. And if you add them, the denominator will be same. So if you add the numerator, you will get this term square plus this term square, and in the denominator you have square root of this term, and square root of this term in the denominator and that term itself in the numerator. So the square will be cancelled out and you'll have this term only in the numerator. You can actually do that. This is very simple. Should I do that? I'll just write down the value of cos 2 theta and sin 2 theta here. You can do the substitution later. Cos 2 theta, I think it's time for you, right? 12. You have a class at 12?
Yes, sir.
Okay. So I'll stop here. I'll just write down these angles. The cos 2 theta will be sigma x minus sigma y by 2 divided by tau xy square plus sigma x minus sigma y by 2 whole square root. Sin 2 theta will be tau xy divided by this term. Now if you substitute 2 of this here, you will very easily see that sigma x dash maximum value of sigma x dash will be sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 whole square plus tau xy square. This is what you get if you do the substitution. Similarly, you will get sigma x dash minimum as sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 whole square plus tau xy square. So this is the equation you will get if you do the substitution. Same thing can also be done for shear stresses. We have found out the maximum value of normal stress by finding out the derivative and equating it to 0. The same way we can find out the maximum value of tau xy dash by finding the derivative and putting it equal to 0. So this is I have written down the equation. Yes, tau xy dash. So find out the derivative and equate it to 0. This is quite straightforward here, I think, and you will easily get the value tan 2 theta value for maximum value of shear stress will be obtained using this equation here, tau xy. So just like the previous case, if you back substitute 2 theta into the equation, you will find out that maximum value of maximum or minimum. If you find the derivative, you'll get maximum or minimum, right? So maximum or minimum value will be plus or minus sigma x minus sigma y by 2 whole square.
Hello, sir.
Yes.
we have another class now.
Okay, I'm concluding. Okay. So we'll stop it here. We'll continue it in the next class. Okay, just a second. Regarding attendance, give me a second. You can go ahead and join that class. Okay, I'll just put the link for attendance in the WhatsApp group. Okay.
Thank you, sir.
So you have. I'll give you some time for filling out the form. Let's see that. Okay, forgot to start.